Hello everyone, welcome to Pressgrade. Today we are going to discuss the IP routing. What is IP routing? Um, Algorithm of the IP routing, router architecture. What is the routing processor, switching, and static routes? And there are some of the use cases. So now, what is routing? So routing is a process of moving packet from one network to another along the path from source to the destination using the routers. So as you see here, this is a computer A. Want to send or talk to computer B. How it will packet will be forwarded? It can forward from, there are two routes, right? One, or it can go from here to here, and this is the second route. So routing is a process of moving packets from one network to another along the path from source to the destination using the routers. So in this, from computer A to computer B, you can see there are multiple routers, right? There are two paths, and in this path we have two routers, router 1 and router 2, and in the second path we have router 3 and router 4. Now let's take an example of another, right? IP routing. For an example, from here the computer wants to reach to the IP 47.1.1.1. How it will works? First it take a look at the routing table of this router, and it says, hey, if this network 47.1, it needs to forward it from this port serial number 1. Then it's forward from here, and then at this router again, it's take a look at the routing table, and in the routing table you see again here 47.1, it needs to forward it to this path, right? This serial port. So it's forwarded right here. And then at this router again, the routing table, look at it 47.1, and it says, hey, you need to forward it to this path. And this is how packets forwarded from one network to another, right? So to be able to route packets, a router must know the destination address, right? If you want to send from packets from one network to another, router must know the destination address. As we see here, this router knows the destination address. Like if there is a route coming from 47.1, forward it to this way, right? So it knows the destination address. And also neighbors routers from which it can learn about remote networks. So possible routes to all remote networks and the best route to each remote networks, and how to maintain and verify the routing informations. So IP routing process is like IP routing with the HTTP server or ICMP error, an IP packet with the destination not in the routing table, and IP routing using the MAC and IP addresses, right? It use the MAC or like IP addresses in the routing table. What we use? IP addresses. So now if you take a look at here in simple diagram, what is routing? Routing involves two activities basically. Run routing algorithm protocol. So routing algorithm determines the best path for data to travel across the network, right? Routing algorithm determines the best path for data to travel across a network. In other words, determine the optimal path or the best path for routing packets from the source to the destination network, right? It can be very complex. Now here, think about the GPS navigation system, right? When you want to drive from point A to point B, the GPS choose the fastest route based on real-time data. Similarly, router use the routing algorithms to determine the best path for data packets, right? And there are some common types like distance vector and link state. We'll learn into later sections. So switching. What is the switching? Switching moves packet from input of the router to appropriate output of the router. Relatively straightforward, right? This is switching is relatively straightforward. These are the two main activities in the routing algorithm and switching. So this is the another like router architecture, right? If you see, there are some input ports in the router. This is the router. Okay, in this router there are some input ports and there is a switching fabric, and you said the routing processor, and there are some output ports, right? So switching fabric, what is switching fabric? Switching fabric refers to the hardware mechanism that actually moves data from one port to another with a switch or router, right? So it's this is a simple mechanism. It's very straightforward. It's moved from input port to output port. That's it. In other words, like real-time example, imagine a busy airport with the multiple gates and terminals, right? The switching fabric is like the pathways between terminals where passenger travel. So instead of passenger, we have a data that travels in the terminal, right? In a network switch, it internal mechanism that connects incoming and outgoing ports. There are two types, right, in the switching. Data takes dedicated path, that's like a circuit switching, and packet switching. So packet switching is data is divided into packets that may take a different paths. So packet switching is data is divided into packets and that may take a different paths. So what is a routing processor here? Routing processor maintains the routing tables. Now we'll learn what is a routing table, right? It moves the packet from input interface to output interface with the help of switching fabric, right? So this is the routing table of the router. And it's look at it, hey, if any networks for 192.168.2, then this is the next router, like this is the interface if. And again, there are two common types, distance vector and link state. Distance vector is RIP and link state is OSPF. That we'll learn it later in the dynamic protocol section after like one labs. So switching uses packet switching based on a statistical multiplexing. A resource are shared and queued for resources. This is how the switching works, right? And there are now four sources of delay in the network, right? Of course, if you take a real-time example, when you are traveling from point A to point B, there are some traffic, right? So what are the delays in your when you are traveling, when you're using the GPS? Traffic, right? In some areas we'll see more congested network, right? When you are traveling in the freeway, you see there is a less traffic, but again your GPS take the paths where is the street, and you get into the busiest street, right? And that has only one lane, and the traffic increases, right? Or there are signals, right? Some of the intersection, so you need to stop at the signal. So those are the delays. The traffic is one delay, and you change from, let's say, in freeway you have 60 mile per hour speed limit, and when you enter into street or boulevard you have 40 mile or 30 mile per hour speed limits, right? So those are the delays. So and there are some signals, so you need to stop at the signal. So those are the delays in the real time example. So similar way in the network we have transmission delay. So what is the transmission delay? Time it takes to push all the bits of packet onto the transmission medium. That's a transmission delay. And for an example, if you are sending a 10 Mbps file over a 1 Mbps link, right? And there is a 1 Mbps link file, or let's take an example, you have 1 Gbps link and you are sending 1 terabyte of file. It's a huge file, right? And the transmitter delay is how long it takes to push the entire file out of the sender's computer to the destination, right? This is the destination computer. Or in other words, you take it, this is the 1 Mbps link, and you need to send a 10 Mbps file to this one. So transmitter delay is how long it takes to push the entire file out of the sender's computer, right? That's a transmission delay. And now what is the propagation delay? So propagation delay is time it takes for a signal to travel from the senders to the receiver. So this is the sender, right? And this is the propagation delay. Time it takes for a signal to travel from the sender to receiver. And for example, receiver is the send, right? So this is the propagation delay. And you see the transmission delay, it's here. So example, this is the example you see, right? And what is the nodal processing delay? The time taken by a router or switch to process the packets, right? When we just saw the router has a routing algorithm and router processor, so time it takes to process the packets. It checks its header and makes a routing decision, and then it look into routing table and where it needs to forward it, right? And then it take the decision. And queuing delay, right? Now let's take an example of the queuing delay. What is a queuing delay? Queue, it's very simple, right? When you heard the word queue, what do you think? Like if you want to get on the bus, right? There is a queue, long, right? People. So it takes time to get on the bus. So in similar way, time a packet spends waiting in a queue before it's processed or transmitted, right? So if the computer B and computer A wants to send packets, they basically spend some time in a queue, right? And that's a queuing delay. If you are in a line for another word like a coffee shop, right? And you desperately need the coffee, but there is a huge line, right? At the Bluestone Coffee or there are your favorite coffee store. And you need to wait for some time, 10 minutes, right? So that's a queuing delay. So these are the delays in the networking. Now routing, basically it has a complex crucial aspect of packet switch networks. And what are the characteristics of required? Correctness, right? We need to correctness, simplicity, robustness, stability, fairness, optimize, efficiency. A routing protocol is used by routers to dynamically find all the networks in the internetwork and to ensure that all routers have the same routing table. This is what happened in the routing, right? So routing protocol is used by routers to dynamically find all the networks in the internetwork and to ensure that all routers have the same routing table and determines the path of a packet through an internetwork, right? And routing protocol can be used to send user data through the established connection, assigned to an interface and determine the method of the packet delivery. Now there are two types of routing protocol, static and dynamic. So today we are going to learn mostly static, what are the static use cases, and advantage, disadvantage, and then we'll do the static routing lab. So you will get hands-on experience on the switching, routing, how to configure the static routes, how to troubleshoot, right? And then after that we'll jump on the dynamic. But let's just understand what are the difference, right? So routing information entered manually. So each command you need to enter manually for the static routes. Routes are predefined and are fixed, so not frequent router changes. So in the static routing, routes are manually set by the network administrator. So if you are a network administrator, you basically need to set manually all the routes. It's like manually setting direction on paper map, right? So this is, consider your paper map, old era paper map, and dynamic is your GPS, mobile GPS app, right? And this is the paper map. Which one is sounds better? This one, right? So, but it's very important to learn the static routes because in some use cases, it's good to use the static route as well. So dynamic routing, like routers automatically adjust the routes based on the network condition using the routing protocols. And what are the Dynamic routing protocols, there is a one called RIP. So there are two types of RIP version 1 and version 2. RIP stands for Routing Information Protocol. And there is one more, OSPF, Open Shortest Path First. And there is one more, BGP, Border Gateway Protocol. And there are two types, EBGP and IBGP. EBGP and IBGP. And there are EIGRP. EIGRP is a Cisco proprietary protocol. It's called Enhanced Interior Gateway Routing Protocol. And there is one more, ISIS, Intermediate State to Intermediate State. So mostly in industry, OSPF and BGP are widely being used. And only Cisco use the EIGRP. But I work for Cisco. In many cases, even in the internal Cisco networks, they are using OSPF and BGP. But there are very rare cases they use the EIGRP. But we'll do lab on each routing protocol. So don't worry. First we'll understand the static routing, what is the static routing and use cases, and then we'll do the static routing lab, right? And then we'll do the RIP lab, OSPF lab, BGP, EIGRP, and ISIS, right? So BGP will keep it at the last because it's very important, okay? So we'll do RIP lab, OSPF labs, right? And then we'll jump into the switching, what are the VLAN, LAN, and then we'll come back to the BGP and do the BGP labs because it's very important. So static routing advantage, right? There is no overhead on the router CPU. This is the huge advantage of the static routing. And it's a cheaper router, right? So if there's no overhead, then if your router CPU is very less, it doesn't require more percentage of the router CPU. And there is no bandwidth usage between routers, so it saves money on the WAN links, right? And it's at the security because the administrator can choose to allow routing access to certain networks. Why? Because the administrator has to manually enter those all commands. If it does not allow, if it does not configure it, then it cannot communicate. So static routing has these are the following disadvantages. The administrator must understand the internetwork and how the routers are connected in order to configure the routes. So basically, network admin must know entire network, what networks, what are the subnets, how they are reaching to the destinations, right? And it must have the entire diagram and with all the details, like how networks are going to communicate. And if a network is added to the internetwork, the administrator has to add route to its on all routers by hand. Basically, you go in each routers and configure it manually. So that's why it's not feasible in the larger network because maintaining it would be a full-time job in itself. Even maintain the one router or one switch, it will require one full-time network engineer. And that's how it became the complex in the larger network. And you know what's the largest network in the world? Internet, because it's a network of networks, right? So that's why. And this is the command we use: IP route, destination network, destination masks, and the next stop or existing interface. Don't worry, we will do this in the labs, but today we are going to just discuss some use cases to better understand. So when we do the labs, you know, these are the use cases, right? And we'll configure all the interface and test it how it works. So default routing, what is the default routing? Default routing to send packets with a remote destination network not in the routing table to the next of router. And default routing on the subnetworks, those with only one exit path out of the network. Default routers as a static route that use the wildcard instead of the network and mask information. So this is the default route. So all IPs are by default is forwarding to this address. It's a gateway. So mostly default router you will configure on the Linux server. If Red Hat or Ubuntu, you will see there is a default router, right? So because you are pointing your server, um, forwarding all traffic to the default gateway, and that's what you do in the Linux server mostly. But you can do it in network as well, router and switcher. So all Cisco routers are class pool routers. Expect a default subnet mask on each interface of the router. And we discussed it, right, in IP addressing. What is the class pool IP address and classless IP addresses? When a router receives the packets for a destination subnet that's not in the routing table, it will drop the packet by default. This is what it does, right? So when router receives the packets and it's look into the routing table and it doesn't find any entry in the routing table, simple, it drops it. If you are using the default routing, you must use the IP classless command because it is possible that no remote subnets will be in the routing table. We'll look into it on the routing like labs. Okay. So route tables. What is a route table? This is the word you will hear a lot in the routing labs. All. So route table is basically nothing but examines what happened when the packets arrive at the router interface, right? If there is a router, it receives the packet basically, then it's examine what will happen when this packet is arrived here. So what router should do it at this interface, right? And how it determine is take a look into the routing table. So data link layer frames destination address fixed is examined, and at network layer, remember routing only understand the layer 3. This is the network layer. Data link layer is the layer 2. The destination address of the packet is examined, right? So what is the destination address of this packet? It examine. If it does not exist in the routing table, it simply drops here. So route entry, each route entry in the routing table must contain below destination address and pointer to the destination address. So you will fully understand we do the routing labs. Okay. So right now, just get yourself familiar. Um, More specific address match. So this is how the descending order works in the routing table. When it look at it, look at the host route, host address is subnet. Group of subnets means summary route or summarized network. Major network number, group of major network number like a supernet, default address. If the destination of the packet is not matched with the routing table, the packet is dropped, right? And it says destination unreachable, ICMP set to the source. What is ICMP? ICMP stands for Internet Control Message Protocol. It's a set of rules that network device use to communicate errors and operational information. So here it's found error, right? Because it did not find the routing entries. So simply packet is dropped. So it send the ICMP message back, right? Hey, there is an error. ICMP is a key part of the Internet Protocol suite. We'll discuss that later in the dynamic labs. So again, routing table, static route written into route table must follow below, like IP routing must be enabled, next hop addresses if used must be reachable, and the exit interface must have an IP address configured on it. The exit interface must be up, right? Directing a static route to an exit broadcast interface without specifying the next hop address can cause excess excessive amount of traffic on the broadcast network and also might eat up the router's memory as well, right? And then it look into like administrative distance, which is measure of preferability, right? So now you will wonder what's the administrative distance. So administrative distance is a value used by routers to determine which routing protocol to trust if multiple protocols provide different routes to the same destination. And that time administrative distance is very useful. Okay. because in the network, complex network, you will have many routing protocols, right? You can have a static routing protocols, and you can have OSPF, right, and BGP. Mostly, if these are the combination OSPF and BGP, or ISIS and BGP. But BGP is must for border network, right? When your corporate network is communicate to internet or ISP, that's where BGP is being used. And mostly OSPF and static routes we use for internal network. So think of it like a person asking for direction from multiple source, right? If person is a professional driver, then it's a OSPF, it's an internal network, right? And you trust their direction more than a stranger. And now what is a stranger is RIP. Its name is same, right? RIP. Now it's not being used anymore in the industries. So the professional direction would have lower administrative distance in this example. So if any interface or any network is directly connected, then administrative distance is zero because it's directly connected, right? And it's the fastest way to reach. And administrative distance for the static route is 1. So that's why static route is the fastest way. But again, it's become too much complex, right, to manage it. And that's why we mostly don't use it, and that's why we need dynamic routing protocols. And dynamic routing protocols RIP administrative distance is 120, OSPF administrative distance is 110. So don't worry, we'll learn that into dynamic protocols. Now let's take an example of static routing use cases, right? So as you see here, there are 4 routers are connected. One is a Carol, Dahi, Lewis, and Baum, right? These are the 4 routers, and you can see each router has a 2 interface, right? This one is Ethernet 0 and serial 1 or serial 0, and this one has a similarly 3 interface right here. This one has a 3 and this one has a 2. So now if you see here, 10.1.1.1 is directly connected. So that's mean administrative distance is 0. And this one is also directly connected. So administrative distance is 0, right? 10.1.2.0 network. And where is the 10.1.3 network? Basically, if you want to reach to all other network, what this router's routing table is saying, next stop is 10.1.2.2. This is the next stop, 10.1.2.2. So if you want to reach, this routing table says, if any networks right here comes and says like, hey, I want to reach to 10.1.6.0, this router will take a look in the routing table and it says, okay, simply forward it to next stop. What is the next stop is Dahi serial 0 interface, 10.1.2.2. So I simply forward it here. And then this Dahi will look into this routing table. Hey, 10.1.7.0. Okay, simply forward it to this guy, right? And Lewis look into the routing table, 10.1.7.0. All right, I do have entry, forward it to here. And it says, hey, 10.1.7.1, this is the directly connected. So it's forwarded to this interface. This is how the routing works, right? So router Carol basically look at it. What is the best match? Complete the process until the packet reach the destination. Routing start point and end point, right? When the routing start here, what is the source address and what is the destination address? So what is the end point? So this is how the routing start. Assumption, it looks for the next stop addresses match to interface. If it's yes, then it's forwarded. It's simply, let's say there's a network, if the packets come here and this says I need to reach 10.1.8.0. Carol will look into the routing table and says like, hey, I don't know how to reach 10.1.8.0. Simply drop and send ICMP error message. basically SAMP failed, right? So we are sending it will not forward that network to this guy. So now there is a command, right? If you do so IP route, then you can take a look. This is how the you will see S means static, C is like a connected, I stand for IGRP, R stand for RIP, B stand for BGP, right? O stand for OSPF. So if we look at it here, this is subnetted 10 dot this is slash 24 is subnetted 7 subnets, right? 10.1.4.1 wired. If you want to go this network, this it says go via 10.1.4.1, and this is we are looking into Levis, right? So if you look into previous example right here, this is the so IP route table, right? So I said if you want to reach to 10.1.0, 10.1.2, 10.1.3, forward it via 10.1.4.1. So this is what exactly we are seeing it here, right? There's three. And now if you see 10.1.7.0 via 10.1.6.2. So if we go back here, you simply look at it here, right? It's via connected right here. But all other these three networks, you forward it to 10.1.4.1 to this network. And now so you see here, this guy, and this guy is directly connected in say serial 1, serial 0 and Ethernet 0, right? Directly connected. 4.0, 5.1 is this one, Ether 0, right? And 6. Is in serial 1. So you see 6.0 is serial 1. This is how you look into the so IP route. So now you know the static IP route command, like how to configure the static IP route and how to look the routing tables. Basically, you do the so IP route and you can take a look at the routing table in the routers. So what are the advantage of here static routing, right? So if we take a look at it here, so some of the routing protocols now no one use the RIP and IGRP, but it cannot route, but static route can does, right? So there is some limitation of this RIP and IGRP, but that limitation does not exist in the OSPF and BGP protocol. So that's why mostly OSPF and BGP protocols are widely being used into network. So what is a discontinuous networks? Basically, it occurs when two or more subnets or networks that are part of the same larger network and are not directly connected to each other. They are separated by one or more other networks or routers, right? Let's say you can summarize 10.0.0.0 in your entire slash 8. This is a part of the larger network, right? And this one and this one. And this one also. But if you want to talk to 10.4.7.1, it's not directly connected. It goes via Tiger router in this way, right? And that's a limitation. But if you use static routes, you can you can configure it by using a static route or OSPF dynamic protocols like OSPF and BGP, because those are the most advanced routing protocols, and those advanced routing protocols can handle this discontinuous networks more efficiently. So if you have to, it's better to use OSPF or BGP, but if it's a smaller networks, you can still use a static route. Static route does support that. Basically VLSM concept, right? We know how to subnet the networks and subnet the subnets, right? So that's a VLSM concept. Now if you take a look at here, what is the routing table of this piglet here? 10.1.68.0 and slash 27. Slash 27 means 255.255.255.224. This is the subnet mask. Remember, this is the subnet mask. and this is the next hop, and this is the like network, right? So in the Piglet, you see IP route. Basically, you configure the network. If you want to reach to 192.168.1.0, basically, who is your next hop? Your next hop is this guy, right? So if you want to reach to any network 192.1.64, that's slash 27, you forward it to this way. Just cleared it so it's easier, right? Now you know these two routes we are forwarding to this way. But if it's a route 10.4.6.0 where you are forwarding, basically in this router you are forwarding all the networks to this side, right? Because this is the side is configured. And similar way in the pool, right? Where you are forwarding all your routes to this gate, right? Because this is your next hop. You see here, your next hop IP is common for this all routes, right? And you need to make sure that this is the IP and this is your network, right? Network address, or we can call subnet, and this is your subnet mask. And this is your next hop. This is how you configure it. And in Tiger, you see it here 192.168.1.0. Where is it? It's this side, right? So you forward it to this guy. So Tiger forward it in this way, right? In 10.1.0.0, this is the slash 16 network. So where you are forwarding, the TigerNet router is forwarding to this way. In 10.4.7.0, it's forwarding to this way. This is the next hop. And similarly with this router, this is the routing table. And now if you do here at the show IP route and at this router, this is what you will see. 10.0.0 is variably subnetted, 3 subnets and 2 masks, right? 10.4.6.0, 10.4.7.0, 10.1.0, and how it is connected. 10.4.6.0 is directly connected on this one, serial 1, and this one via 10.4.6.2, and this one via this guy, right? And similar way in this network, subnetted 3 subnets is directly connected via 165. So now you know the how static, what is the static route commands: IP route, network, subnet mask, and the next hop IP. And how you can see the routing table by using the show IP route. And this is what you see in the show IP route, right? So summary route. So now summary routes, basically single summary routes for several destination address. So 192.168.0. Now if we look into the previous example here, Piglet, right? Piglet, we configure 192.168.1.0, 192.168. So first two commands, you can replace it simply. You can summarize it. So first two commands. These two commands, basically we summarize it here. How? You see here, the difference is the last digit subnet mask. Here we are using a slash 27. But now we summarized here. So our subnet mask is slash 24. So that's why IP addressing is must, okay? If you still think like, hey, you need more practice, please do more practice in IP addressing, subnetting, subnet mask. That's why when we talk about slash 24, you directly know what is the subnet mask of slash 24. And when this is how the summarize works, right? And similar way we summarize this one. Now you see a 255.255.254.0. This is your subnet mask. And here, right, our next step is to, so basically 4 entries. You see here, we enter, initially we do the 4 entries. Those 4 entries can be summarized by using this only 2 commands. But what is the main play role here you need to do? Subnetting, right? So you should know the subnetting. So that's why you can summarize the networks. And you need to configure the less static routes in the router. So similar way you can do it for the other routers as well. And now let's take a look at the alternative routes. So in the static routes, so for an example, similar, we added, this is the new link we added, right? This is the new link. Has been added between these two routers, POO and IGOR, right? So all packets from POO to 10.0.0 network will take this new path, with the exception of the packet destined for the host. Right now, if you look at the POO's routing tables or static routes, how we have configured, if any networks needs to go 192.168.1.192, we forward it to this guy. So this guy, for we are using triggers this is the next stop we are using for 2 networks, 192.168.1.192 and 10.4.7.225, like 10.4.7.25. So if any packets wants to reach to this IP address, then how it will travel? Let me just change the color. Right, if any packets, let's say the one packets came here, right, and says, hey, my destination IP address is 10.4.7.25, how it will travel? Basically, it's look into your routing table. This is the routing table, and it says, okay, my next stop is 192.168.1.66, so it's forward to this way. And it look at the here routing table and says like, hey, I need to forward this IP to this way. So it goes here and it's reached to here. This is how it travels. But all other networks traffic of 10 dot. Other than that, any IP come right in this subnet. If any other IP is in this subnet 10.0.0.0, right, or let's say 0 or 10.1.0.1, if this is the destination IP, how it will travel? It will go via this way, and then it will look into here the routing table, right? And if it's 10.1.5.1, let's say this is the new packet came and it says, hey, my destination address is 10.1.5.1. So it simply go this way and forward it this way. Okay, this is how the alternative routes works. So what are the characteristics of the static routes? Reverse direction. First, if the network topology changes, right, we change the network topology, that means you need to change the routing configuration in this router and each router. So routers that are required to know about these changes must be reconfigured, right? Second, static routes can be used to create very specific routing behavior. So perhaps indesirable to have traffic taking one path in one direction and another path in opposite direction. So we take a look here. If the packets comes for 10.4.7.25, that goes from port to Tiger, this one, and from there to here, and from here it's reached to right here. but all other packets goes via this way, right? It's directly connected, so it takes this path. But only this guy takes a longer path, right? It goes right here and then go. So it basically adds one additional hop. Now we can simply take a look here, right? You can do debug IP packets. This is another command to debug IP packets, and you can see how packets are going forward, right? Traveling. You see a 10.4.7.25 directly connected, right? And it's forwarding to this way. Now let's take a look at the floating static routes. So what are the floating static routes? Basically alternate routes, right? So unlike other static routes, a floating static route is a less preferred than other routes in the routing table. It appears in the routing table only under the special circumstance of the failure of more preferred route. So now if you see here, piglet and rabbit, right? There are two routes are here, this one and this. So you can configure this one as a floating route. So if this link goes down, then route will use this path. Once this link was come back, then again route will take this path. And it uses the summary address along with the floating static routes on the routing tables. And administrative distance measure or preferability, right? If let's say both links are up, who will decide? AD, administrative distance. You can configure the administrative distance, right? For static route, administrative distance by default is 1. So what is the administrative distance? Is a value used by routers to determine which routing protocol to trust if multiple protocols provide a different routes to the same destination. The lower the AD, the more trustworthy the route. Remember, whatever, if you see the administrative distance is lower, basically that's your trustworthy and best route. And now let's take a look here, right? This is the piglet and rabbit. So now in the rabbit here, we take a look here. You see these two are directly connected via serial 0. We go here and let me clear this out. Right? Those are directly connected here via serial 0. And now if the serial 0 goes down, basically someone unplugged it or cable goes bad, right? If someone damaged the cables, like, then what will happen? That link will go down basically. Now if link will go down, you see here these two routes are via that, but now you see here the route table entry change, right? It takes effect through 10.1.20.0, 10.1.20.1 instead of 10.1.10.1. So instead of going through this route, because this link failed, so it will go through this one, right? And now if you simply you bring back up the serial 0, what will happen is goes back to your original state, right? It's like, hey, now I know the link serial 0 is up, so I want to stop forwarding via this way. It will go via this link. So these are the floating state routes. But now how we can do it better, those floating state routes, and how we can use better utilize this bandwidth, right? In current situation, you are just using you have two links, but you are only using one link, right? So fully wastage of the one link because you are not utilizing, right? When you are utilizing, when this link goes down, so you are not utilizing fully the both links at the same time. So what should we do? Load sharing or load balancing. So load sharing allows routers to take advantage of multiple paths to the same destination by sending packets over all the available routes. So there are two types of load sharing or load balancing: equal cost and unequal cost. Equal cost basically load sharing distribute the traffic equally among multiple paths with the equal matrix. Load sharing is also called load balancing, right? And simple unequal cost means load balancing distributes packet among the multiple paths with a different matrix. The traffic is distributed in inverse proportion to the cost of the routes. And this path with the lower cost are assigned more traffic, and path with the higher cost are assigned the less traffic. This will learn into dynamic protocols like OSPF and BGP, how we can do the load sharing and cost balance, right? Unequal cost and equal cost. Static routes which have no metric supports only equal cost load sharing. So static route has a no metric, so it supports only equal cost sharing. Again, static routes supports only equal cost load sharing, and dynamic protocol supports both equal cost and unequal cost. So basically, equal cost means here Rabbit routers wants to send to Piglet 10 packets. What it will do? Equal cost means it will send one packet from this way and one packet from this way. Again, it will from second packet from this side and second from this side. So if you are sending 10 packets from here to here, so 5 packets will go from this route path and 5 packets will go from this path. So that's a equal load balancing, right? And now you have cost configure in your dynamic protocols. So that's where you define like, hey, this link, let's say it's a 1 gig link and this is a 10 gig link, right? So I want to send here only 10% of the traffic. 90% of the traffic you want to send it via this way. So you can do that by using the coast in the dynamic protocols. We'll learn that in the dynamic protocols and dynamic protocol labs. And simple. In static routes, you have equal load balancing. So simply, what should you do? You should simple configure the static routes, right? You know the static route protocols: IP route, network, subnet mask, and the next hop, right? So for 10.4.0.0, this is here we use the /16 subnet mask 255.255.0.0. And what is our next hop? We have two next hop, right? 10.1.10.1 and 10.1.20.1. So if we go back here, so if you want to reach to 10.1.4. Right, then it simply says like, hey, use this one as a next hop and this is as a next hop. So you use both equal load balancing. Static route, equal load balancing. So it's a simple command that you configure it: 10.1.10.1 and 10.1.20.1. Simple for 10.1.5.0, right? You configure, you provide basically two next hop. So that will automatically configure as a next hop. And this is the SWIP route commands you see here. If you want to reach to this network 10.1.5.0, and there are two ways to reach, and both has a equal load balancing. You see here 1/0, 1/0. So you can reach via this and via this. So if you are sending 10 packets, basically 5 packets to this and 5 packets to this routes. Similar for this one, 10.4.0. You can go via this and this route, and similar way here, right? So this is the equal load balancing. So when you see the two links, simply you configure the next hop, all your traffic via this and this one. Same command, but your next hop will change, right? What will happen? Your next hop will change. Your next hop IP is changed here, right? your next hop IP is 1 here, and for the same network you define the, so now the Rabbit router routing table knows that, like, hey, if I want to reach to 10.4.0, I have two paths to reach, and it's located like, hey, I have configured the static route, so it's equal course, right? So if you receive the two packets at the same time, it will forward via one this way and second via this. Now load sharing in Cisco Express forwarding. What is the load sharing? Is also either per destination or per packet, right? Per destination load sharing is distribute the load according to destination address. And this is the default type of load sharing used by Cisco Express forwarding. Cisco Express forwarding default switching mode for IPv4 does not use for IPv6 efficient switching process and builds a forwarding information base FIP. Now, what is the recursive table lookups? The case study. This is the case study. This is interesting, right? All route entries do not necessarily need to point to the next hop router. Now we learn in our rep, right? Whatever routes we are configured, we basically configure it to the next hop IP. But again, in the static route, there's a option that you can configure recursive table lookup, so you don't have to configure the next hop. You can configure your next hop is the next router is the next hop. So originally our command was here, whatever POO send this network traffic, it goes via this way, right? But now instead of this next hop, we can take a look of the Tigger's net routing tables, that's called recursive table lookups, and configure the Tigger's next hop. So in a networking, recursive table lookups refer to the process where a router, in order to determine the best path for a packet, may need to perform multiple lookups in its routing tables, right? And this happens when the next hop for the packet is itself determined by another lookup in the routing table. So key point here, the router doesn't have a direct route to the final destination, so it look up the next hop. So this router doesn't have, let's say 10.1.30.1. Packet came and said, hey, my destination address is 10.1.30.1, and this one doesn't have routing table, right? So this router POO can take a look of the Tigger's routing table. That's called recursive table lookups. And if next hop is also not directly reachable, it performs another lookup to find a path. It can take a lookup on this one to find a better path, right? And this process continues until the router finds a direct route to the destination or the destination is reachable. And then it's take a look up this router and says like, hey, 10.1.30.1 is directly connected to this interface. So I found it. So in this case, there was 3 recursive table lookups, right? So definitely, if you want to increase the performance, you want to reduce the recursive table lookups. Now if we do here show IP route, now you see here 10.0.0.0/24 is subnetted to subnets 10.1.10.0, 10.1.30.0. How they are configured? They are via configured 10.192.168.1.94. Where is this IP configured? It's configured at this place, right? 10.1.10.2. That is here. So we did recursive table lookups here and this router. Okay, this is the use case again. So again, let's configure this senders for recursive lookups and enable the network administrator to redirect all of the that routers exist traffic from the Appleman to like WSDL by changing one route entry. So if you configure show IP route 10.87.14.0 via 10.23.5.95, and then you need to configure no IP route 10.87.14.0, and you says, hey, no IP route, so I remove this network. So I configure this route and remove this guy. So now if any networks forward the traffic, it will go via this way. Let me clear it here. Let's take a look. Don't worry about these two commands yet, right? Let's take a look here. So if you want to reach to 10.45.2.0, where is it? It's here, right? And what says senders, hey, my next stop is 10.87.14.1. This is the next stop, right? 10.3.0. This one, who is the next stop? Our next stop is common till here, right? So senders know, like, hey, if I want to reach, my next stop is this. So it start forwarding traffic to this side, right? So initially it's equally configured, but as soon as you enter this commands in the sender, these two commands, it will stop sending routes to this guy. Okay, it will send traffic via this way, because our next stop is, we are using the recursive table lookup. So here you can manage it, right? Like, hey, now your next stop, you change it. So similar way for this routes are configured here, and we define our next stop is this guy, right? And same, these three routes, next stop is this. And now this is the main command, right, that you use. How to reach this network 10.87.14.0. We said, hey, you reach 10.23.5.0. So we use the recursive table lookup for here, right? And 10.87.14.0. If you want to reach this guy, how you reach? You go via this way. So all your traffic is going via this way. But now you enter these commands, IP route 10.87.14.0. Assume that you entered this command. What will happen? Now you have two static IP routes, right? One is this and second is this. So that will start doing equal load balancing basically. But as soon as you enter this command, what happened? As soon as you do no IP route, basically you are removing this guy. So then there's no equal load balancing, and you will start sending traffic through this router. Like that, okay? And what are the most troubleshooting for static routes, right? So these are the questions you should ask. What does the router know, right? How long has the information been in the routing table? Like, does the router know how to reach the destination? Is the information in the routing table accurate, right? If there are any errors, you must know the routing table is accurate, right? And router knows how to reach the destination. And knowing how to trace a route is essential. So there are two troubleshooting commands, trace route and ping. And ping, right? So what is trace route? Trace route is a network diagnostic tool or like command that shows the route path. It shows the detailed route path that packets takes from your source to the destination. So it shows each hop along the way, which can help identify where the delays are and problem occurs in the network. So how it works? So traceroute send a series of ICMP echo request packets similar to the ping with incremental increasing time to leave value. Each router that handles the packet reduces the TTL by 1. When the TTL reaches 0, the router sends a time exceeded message back to the source. This is the process allows trace route to map out each hops along the path to the destinations. Okay, I will show you how we do it when we do the static routing lab. How to do the trace route and the ping. So what is a ping here? So ping is a simple again same protocol, or you can say to test the reachability of the destination host. Right. So ping also use an IP network. It sends a small packets called ICMP echo request. Ping also use the ICMP echo request to the target and wait for the ICMP echo reply. It says ICMP echo request and it's wait for the ICMP echo reply. This round trip time, right? This is, let's say, source, and this is your destination. It says ICMP echo messages, right? It sends bunch of ICMP echo requests, and then it waits for to reply the same ICMP. Reply, and this is the echo, right? You send the ICMP packets and wait for ICMP echo reply. Is measured to determine the latency between your device and the destination. So if it takes more time, then there is a latency between your network, right? The faster the reply you get, that's how you have better uh, basically performance of the link or networks. So simple. The trace route fails, right? Then this is what we see here in this routing table. You see IP route 10.0.0 is directly connected, 10.4.7 we see 10, and but we see here slash 27. And now if you want to reach to this guy, because it's not it here, right? So this router doesn't know how to reach this subnet, and that's why trace route failed. Now let's take a look at the protocol conflict. A host route directs packets from root to milne. Now, if you see here, this router sends the direct packets from here to this guy via this top Ethernet, right? E1. Avoiding the occasionally congested bridge, after the static route was added, the packet routed through root no longer reach the server. Now packets routed through Kanga no longer reach the server, although no changes were made to this router. So what we do, check the IP routing tables, right, of this one and this, right? If there is no change here, you take a look at the IP, so IP route here, and then you do the trace route. So when you do the trace route, what we do, trace route it at here, right? You simply use this trace and then do the IP addresses. This is our destination IP address. So use a trace, this is the command, right? The trace and your destination IP. What is destination IP? This is our destination IP 172.16.20.75. So you can, if you type escape in your command line of the router, then basically you get out of this command, right? It will exit it. Now if you see here, first packet sends 172.16.21.2, it's sent, right? It's reached here, and you see this is the time, right? It's reached, and again it sends the second packet, right? 160 172.16.20.1. That also gets, right, this is the here, it's a reply to go back there, right? So what's this means? Kanga is forwarding the packet back to the root instead of delivering to the correct destination. Instead of sending it via this way, it's again forward back here. This guy say like, hey, I want to reach to this. This is my destination address. It's reach here. So Ru says like, hey, you must know the route to this destination. So it's reach here, but again it's forward back to this guy, right? So there is a protocol conflict. Now Kanga mistakenly believe that is E0 interface of Ru is Milne. So this is what happened, right? Packets goes from this way, but this one mistakenly believe that E0 which reach here, but instead of it goes back this way. So there is a loop. So how we can configure it? Basically here we need to enter this command. Inter Basically you go into interface E0 and no IP proxy ARP. You do here no IP proxy ARP, and then you configure ARP, and what is IP 172.16.20.75, and you define the ARP address, right, NARP, and that's what you need to configure. No IP ARP, you need to configure ARP address, you need to configure it here in the Kanga. So this is what you do, right? You configure interface at here, and at the Kanga you configure this command. And what happens next? And then you do the show IPR, and you can see the IP tables, right? Now it says there's 2 right here, Ethernet 0. So it will forward it to this way. Thank you so much. And next is we are going to learn. Uh, we are doing to, we are going to do static routing labs, and after that we'll deep dive into dynamic routing protocols. What are the types, right? Or RIP, OSPF, BGP, EIGRP, ISIS. Those are the routing dynamic routing protocols, and each routing protocols will do the labs. So now next is the labs. We'll set up how to set up the labs, right? How to configure it, each router and switches, right, or computers, IP addressing. So we'll do the playground, and then we'll do the state routing labs. Thank you.